session, right. So, in the last session we discussed about the basics of polar plot and we had seen how to draw polar plot for an transfer function. Okay. So, last time we were observing the open loop transfer function, we were calculating its mod, calculating its phase and varying omega from 0 to infinity. Okay. So, last time whatever example we had seen, in those example there were no poles lying on the right half plane and there was no 0 present in the transfer function. So, in today's session we will discuss certain different more example of polar plot to enhance the clarity, and then we will discuss about the stability from polar plot, and then we would like to see what is the meaning of enclosement of critical point in the polar plot. Okay. So, here this is our numerical. So, we would like to see this is my transfer function G s equal to 2 over s minus 1, right. So, whenever I am getting what is my type here, my type of system is you can say is type 1 because one pole lying at the origin and order is here it is 2. So, what would be the polar plot? So, from the previous concept we can say for type 2 my polar plot start from minus 90 and terminate at minus 180. So, I will do this plot like this. Okay. This is for type 1 and order 2 system. Okay. So, this concept was valid whenever our all the poles lying in the left half, but here this pole lying in the right half plane. So, this concept is absolutely wrong, we do not have to follow here. Okay. So, that concept was valid only valid whenever our all pole lying in the left half and there should not be any 0 in the transfer function. If there is any 0 and all the pole lying in the left half, so we have to follow all the basic step that we had seen in the last session. Okay. So, here to draw the polar plot we need to make those steps. First step 1, replace s by j omega to obtain the sinusoidal transfer function. So, g of j omega would be given as 2 over j omega multiplied by j omega minus 1. Okay. Now, I need to determine its magnitude mod of g j omega, it is equal to 2 over omega multiplied by omega square plus 1. Okay. Then I need to determine here phase mod of g j omega. So, phase from numerator is 0, j omega is here, it means minus 90 and sorry plus 90 and plus it is j omega minus 1 and this will gives me the phase of 180 minus tan inverse of omega. Okay. So, this thing we had discussed during the root locus also, how to determine the phase of this type of situation, okay, or this type of you can say expression. So, if you like to see, please revise the root locus angle and phase condition, then it would be very clear how we can write this phase as 180 minus tan inverse omega. Okay. So, I can write here it as 180 minus tan inverse omega, and if I shift this phase in numerator, this will become minus 90 minus 180 and plus tan inverse omega, and you can say this is minus 270 plus tan inverse omega. This is my phase. Okay. And here this axis is basically my GSHS. So, I need to plot here imagery of GSHS in the y axis and real part of GSHS in the x axis. Okay. So, I need to make this table for omega equal to 0 and infinity, we need to observe magnitude and phase both. So, when I put for magnitude omega equal to 0, okay. So, here my phase or you can say the my mod value would be infinity. When I put here my omega equal to infinity in this expression, then my magnitude would be 0, directly you can see. Okay. Now, what about my phase? So, for phase omega equal to 0, this is minus 270 and for omega equal to infinity, this is minus 270 and plus this is 90 and this will make total of minus 180, right. So, how we have to move in the polar plot? So, at omega equal to 0 we are getting this phase of minus 270 and magnitude is infinity. Okay. So, I would like to see where is my minus 270, this is my 0, minus 90, this is minus 180 and minus 270. So, I get this angle minus 270, it means I need to start from here. Okay. And what is the magnitude? This magnitude is infinity. So, I can take any shape of any value, right. So, it does not mean whether it is small or large, because it is infinity, right. Now, I need to terminate at minus 180. So, how I am moving from minus 270 to minus 180? If I add plus 90 in the minus 270, then I can achieve the angle of minus 180. This plus sign means we have to move in anti-clockwise from minus 270 to reach minus 180. You can see there is two paths, one is this path, second is you can go from here and go from here, then you can reach to the minus 180. Which path we have to choose? Depending on this sign. Okay. If it is plus, it means we need to move in clockwise direction, sorry, anti-clockwise direction. So, from anti-clockwise movement, I can directly reach from minus 270 to minus 180. So, I start from here, my magnitude is infinity and I need to terminate at minus 180. Okay. So, this is the polar plot for this transfer function. Here omega is 0, my starting point, here my omega is infinity, my end point. Okay. I hope this concept would be clear to you. In the same way, we can discuss our next expression. So, here G s equal to 10 over s plus 1 over s plus 10. Okay. Again here 0 is coming in the picture, it means we need to follow all the steps. I will replace s by j omega to obtain a sinusoidal transfer function. So, g of j omega is given by 10 of j omega plus 1 divided by j omega plus 10. This is coming. Now, calculate mod of it, g of j omega, this will be 10 under root of omega square plus 1 divided by omega square plus 100. This is coming. The same way, I would like to know what is my phase, mod of g j omega. This phase would be you can say from numerator it is tan inverse of omega and from denominator it is minus of tan inverse of omega by 10, right. So, now I need to vary this omega from 0 to infinity for both magnitude and phase. So, first I will deal with magnitude. When you put omega equal to 0 in this expression, what would be magnitude? You will found directly it is 10, it is 1 divided by omega is 0 under root 100 it 10, it is equivalent to 1. So, at omega equal to 0 my magnitude is 1. When I go for omega equal to infinity, I need to solve it. I will take omega square from the bracket. So, 10 omega under root 1 plus 1 by omega square. In the same way in the denominator, I will take common omega 1 plus 100 by omega square. This will cancel out. If I put omega equal to infinity, I will get here value 10. So, at omega equal to infinity, my mod is 10. It means whenever I begin this polar plot, mod is 1. When I terminate this polar plot, my mod is 10. Okay. Now, what about phase? When I put omega equal to 0, 0 minus 0, my phase would be 0. When I put omega equal to infinity, this will become plus 90 and this will become minus 90 and again I will get here 0. Okay. So, what we are getting? It means our polar plot is starting from phase 0, terminating at phase 0 with starting value of 1 and final value of 10, right. It means it will be in the positive side or you can say right side of this plane, GSHS plane. So, I am marking this value is 1 and this value is 10. Okay. So, now question is how this plot will reach to 10, whether it will go like this, whether it will go like this, okay. Because we do not know how we are going to 1 to 10, because our phase is 0, it means we have to follow this direction. Okay. So, where we are going in downward direction, upward direction, we need to determine the mid value or you can say you can put here omega equal to 1. Okay. So, what is the value of phase at omega equal to 1? You can say tan inverse 1 is 45 and tan inverse 1 over 10.1 may be around minus 6 and this will be around 39 degree. What about this magnitude? You can say if you put omega equal to 1, this will become tan root 2, and if you put omega 1, this is under root of 101. For approximation, I can choose it 100. So, this will cancel out, root 2 is around 1.4 approximate value, not exact value. Okay. So, it means I am getting here a positive angle, right. It means I need to move from 1 to 10 in this direction. Okay. So, this will not our direction of movement. So, this is the polar plot for this transfer function. So, whenever we are in confusion how we have to move in first quadrant or in fourth quadrant, we have to take the mid value of omega to determine the plot. In the same way, we can take another transfer function g s equal to this much. I will again put s by j omega. I will get here j omega plus 1, then j omega plus 2 divide by j omega whole cube. Now, this mod of this g omega is under root of omega square plus 1 multiplied by under root of omega square plus 4 and divide by omega cube, and the phase g of j omega is given by tan inverse of omega, from here plus tan inverse of omega by 2, then minus, you can say it is j omega cube. So, here 3 poles lying at the origin, single pole contribution is minus 90, it means single 1 by j omega will give us minus 90, double j omega will give us minus 180, triple 1 over j omega will give us minus 270. Okay. So, directly we can use this concept and we can write here it is minus 270. Now, we have to do this omega equal to 0, omega equal to infinity for both magnitude and phase. So, when I put here omega equal to 0 in the magnitude, then this will becomes infinity. When I put omega equal to infinity, this will become 0. Okay. In the same way, come for phase, when I put omega equal to 0, my phase would be minus 270. Okay. And when I put omega equal to infinity, this will become tan inverse infinity plus tan inverse infinity, right, minus 270. This is 90 plus 90 minus 270, and this will gives me minus 90, right. It means my phase at omega equal to infinity is minus 90. So, how much add in I will add in minus 270 to achieve minus 90. So, you can say it is around plus 180, plus sign is coming, it means I have to move in anti-clockwise. I will start from minus 270, terminate at minus 90, total phase coverage would be 180, in which direction? In anti-clockwise direction. So, I will start from here. What is the magnitude is infinity. So, I can take here any radius curve, right, and it will terminate at minus 90, my mod is 0. So, I will touch origin in the direction of minus 90, sorry, this will be the direction, I had done the opposite direction of it. Okay. So, this is the polar plot for this transfer function. In the same way, we would like to see the special case whenever we are dealing with the higher order polar plot, okay, where we are getting s cube, s plus 2, s plus 4, you can say s plus 1 is here, the order is going above 3 and 4, then what would be the polar plot. Okay. I need to determine first, replace s by j omega, g of j omega is equal to j omega plus 1, same step, and replace s by again j omega, this will be cube, this will be j omega plus 2, and this will be j omega plus 3. Now, determine mod of j omega, this is under root of omega square plus 1 divided by j omega cube, it will remain same, it is under root of omega square plus 4 multiplied by omega square plus 9. The same way, if I calculate its angle phase, it is given by tan inverse of omega from here. Again j omega cube is coming, it means minus 270, j omega plus 2 minus tan inverse omega by 2 minus tan inverse omega by 3. Okay. So, again same operation, put 0 and infinity for mod and phase. When I put omega equal to 0 here, my mod would be infinity. When I put here infinite, my magnitude would be 0. Okay. And for phase, if I put 0, my phase is minus 270, it means minus 270 is my starting point. And when I put omega equal to infinite, so it is 90, minus 270, minus 90, minus 90. So, this will cancel out and this will make minus 360 or 0 degree. So, here I need to terminate in the angle of minus 360. I will start from here and then I have to go like this. Okay. So, whenever we are dealing with higher order, so we have to keep in mind, we have to check the mid value of omega in between, whether we are going in right direction or not. Why I follow this? Because my initial phase is minus 270, final phase is minus 360. If I have to move minus 270 to minus 360, what I will do? I will add here minus 90. The minus sign is here, it means I have to move in clockwise direction. That is why I had moved in this direction. Okay. So, this is the clockwise rotation. Now, we have to see, this is the s cube is coming in the denominator is higher order. I need to check what will be its value of omega if I put omega equal to 0.1. If I put omega equal to 0.1, what would be phase? So, in this expression I will put omega equal to 0.1, tan inverse 0.1 minus 270 minus tan inverse 0.1 by 2 minus tan inverse 0.1 over 3. If you calculate, you will observe this phase is approximately you can say at 0.1 is this phase will come around minus 268.8. Okay. When I put omega equal to 0.2 in this expression, I will get minus, my phase would be minus 260. When I put here omega equal to 0.9, this will gives me the value of, you can say for 0.2, I am getting here minus 268 again, and if I put here omega equal to 1, then I will get, this is coming at 0.9, and for omega equal to 1, I am getting here this phase is minus 270. When I put here omega equal to 1.2, I will get here 272.3 something. So, this is my phase variation, right. So, what I was expecting, to whenever I am starting from minus 270, I need to terminate in this axis. It means, when I put omega equal to 0.1, it should be 271 something, but what is happening? It is minus 268, it means it is coming somewhere here, right. If I have to move from minus 270 to minus 268, how much value I need to add? It is around plus 1.8. Plus means we have to move in anti-clockwise instead of we have to move in clockwise direction. Further, if I am moving omega equal to 0.2 minus 280, I have to move further in anti-clockwise direction. Whenever it is minus 0.9, whenever omega is 0.9 minus 268, it means my phase is reducing, it means I need to return back. Again at 1, my phase is minus 270, right. So, from where we started, we are going again. Now, after 1.2 omega equal to 1.2, what is happening? My phase is 272.3. It means I am standing at minus 270, I have to go minus 272.3. It means I need to add something minus 2 value. It means this minus 2 value is again what? With minus sign, it means we need to move in clockwise direction instead of anti-clockwise. So, we have to move in clockwise direction, and as I keep increasing value of omega, and it will terminate to 0. So, this will be polar plot for this case. Okay. So, I need to determine what value of omega is here. Okay. So, we already determine here when I put omega equal to 1, then this polar plot touches minus 270 line again. So, here my value is omega equal to 1. If you do not know what you can say, you can check this phase expression, put here the line is minus 270 where phase is, and from here this expression calculate the omega, this will cancel out. You can write tan omega equal to tan inverse of omega by 2 plus tan inverse omega by 3. From this calculation you can estimate the value of omega, it will come omega equal to 1. So, this is the polar plot for higher order. So, please always look for the mid value of omega. So, in this case whenever my omega is less than 1, I am moving in anti-clockwise direction. Whenever my omega is greater than 1, so I am moving in clockwise direction. Okay. So, this is about the polar plot. So, now with the help of polar plot we would like to determine the stability of the system. Okay. So, in this case I am assuming this is the GSHS plane, this is the imagery of GSHS, and this is the real value of or real axis of GSHS. Okay. And then we would like to see the characteristic equation, that is 1 plus GSHS equal to 0. From here we can write GSHS is equal to minus 1. So, this is the critical point that we discussed in the last session for the polar plot, right, and this critical point will help us in determination of, you can say, stability of the system, right. So, for that purpose what I will do, I will make this critical point here minus 1 and then I will make a circle like this. So, this is a unity circle or unit circle. Okay. So, I will make a radius from this axis to this minus 1 and I will plot this circle. Okay. After making this circle, I need to observe my polar plot. Suppose this is my polar plot going like this. Okay. We had seen already where my omega is equal to 0 starting from, you can say, minus 90 and terminating at minus 270. Okay. And here my omega is infinity. Okay. So, now we would like to calculate here omega GC, omega PC. How we can calculate omega PC, right. So, for that purpose we need to see my angle G of j omega is equal to minus 180. So, here in the polar plot where it is observing minus 180, this is 0, this is minus 90, this is minus 180 and this is minus 270. So, here you can see this plot touching minus 180 line at this point. So, at this point if I calculate omega, this will come omega PC, that is my phase crossover frequency. The second term we need to determine here, that is omega GC, gain crossover frequency. It happens whenever mod of GJ omega or GSHS is equal to, you can say, 1, and whenever this and where is my magnitude plot is going 1, intersection of unit circle and this polar plot. So, here if I calculate omega, this will gives me omega GC, that is gain crossover frequency. So, if I see for stability, I know that my omega GC should be less than omega PC. So, here my omega PC is coming something here and my omega GC is coming here. So, it satisfies this condition, it means my system is stable. Now, we would like to go for gain margin. How to calculate gain margin? Then we need to calculate this intercept. You can say this polar plot cutting this real axis, suppose this intercept is x, you can say from this point to this intersection point, right. So, gain margin generally calculate whenever my mod, you can say mod of Gj omega Hj omega at omega equal to omega PC, and this will gives you x. So, omega PC is here, this distance is x and the gain margin Gm would be given by 1 over x. Okay. So, what I am getting from this concept? So, this is the remaining gain present in my system. Okay. So, if I utilize, or I can further increase my gain of the system beyond this point, and I can enhance the performance of the system. How to calculate the phase margin? So, phase margin generally calculated by phase angle of g j omega at omega equal to omega g c. So, where is omega g c is here? I need to measure this angle, you can say straight line, this angle is phi. So, when I calculate this angle will come phi, and phase margin would be given by 180 plus phi. Okay. So, in this way we can calculate phase margin and gain margin from polar plot. Second case we can see whenever this polar plot crossing this -1 point, right. So, here this intercept is x, my gain margin would be 1 over x equal to 1 over 1 in dB, it is 0. The same way if you calculate the phase margin, this will be 0, and if you calculate here omega g c, this is equal to omega p c, this is the condition of margin is stable that we had discussed in the previous session. So, when polar plot intersect -1, so this is you can say a margin stable system. Second case, unstable system, whenever our polar plot exceeding this -1, in that case our omega g c would be greater than omega p c, and my system would be unstable and my gain margin would be negative. It means I have to reduce gain by this value to make my system stable. So, one more concept is coming here, concept of enclosement. Okay. So, whenever a curve is here and two points are here, one is A and B, whenever my point lying on the right side of the curve, so we can say B is enclosed by this curve, where A is not enclosed by the curve. So, if I observe my polar plot, suppose this is critical point -1 and my polar plot going like this. So, this polar plot enclosing -1, it means my system is unstable. Whenever my polar plot is not enclosing -1, my system is stable. Whenever my polar plot intersecting this critical point, then we can say my system is marginally stable. So, this is the principle of enclosement that we can learn from this concept. Okay. So, thank you for today.